Assalamu alaikum. Welcome to the next lecture. So, in this lecture, I will be continuing with the last lecture. So, today I will discuss about the improvement of the transient stability due to series compensation. That's the capacitor series compensation. These are two systems where one system is without compensation, other is with compensation. So, when a disturbance occurs, like we have a three-phase fault, so in that case, you can see the accelerating power under the mechanical power curve, and the delta curve is even. And here is also because in both the cases this mechanical power will remain constant, and we'll assume it to be the same one, uh, and we'll assume that the fault is cleared in both the times at delta 2. So in that case, this area and this area will be same. Now for this case, since this the area under the curve has increased as compared to this, you will see the area that is covered from this delta 2 to delta 3, that has to be same as that of A2, but that covered area will be definitely before this delta 3 as compared to we can say that will be before the delta 3. So in that case, the area that will remain for it to sweep after this delta 3 and delta S3 for this case will be more. So in that case, we say that the transient stability for a series compensated system will be more as compared to the uncompensated system. So you can see that the margin for the sweeping of the rotor of the generator is more as compared to this one. In general, as I have told you, that by looking at the area under the curve, we can say that if the area is more as compared to the compared one, that is the uncompensated system, we can say the transient stability has improved. And you can see now it is clearly, since this is the curve for the uncompensated system and this is the curve for the compensated system, the area under the curve for the compensated system is more as compared to the uncompensated system. We see that the transient stability will definitely improve. This was about the general introduction about the series compensation, whether it's a capacitor series compensation or we do it by other ways. Sometimes, until now, we are assuming that there's a fixed series compensation with the series compensation factor of k. So here we have assumed it to be 1 by 3. Now, let us try to define some series controllers which are based on the facts. That's flexible AC transmission system controllers. So the first one being being dependent upon the thyristors, which is made by thyristor and other components. So it will be a thyristor controlled series capacitor, TCSC. So why do we go for this? We'll come across that as well. As we know, the series capacitor often offers certain major advantage over the shunt capacitors. It is because the reactive power that is provided by the series capacitor is a function of square of the line current as compared to the reactive power that is provided by the shunt capacitor. It is proportional to the or function of the square of the bus voltage. For achieving the same system benefits as those of the series capacitors, shunt capacitors are 3 to 6 times more reactive power rated than series capacitors need to be employed. So that means for providing the same benefits, or we can say same sort of the voltage control, we need to have shunt capacitors 3 to 6 times rated more as compared to the series capacitors. That's one more advantage of series capacitors. Furthermore, which is one more advantage actually, shunt capacitors typically must be connected at the line midpoint, whereas there is no such requirement for the series capacitors. They can be installed at anywhere between the series, this sending and receiving. Usually, we don't want that the series compensation should be a fixed, or it should be variable depending upon its requirement. Sometimes it may be required as 20%, 30%, 50%. It should not be a fixed one. because it should be dependent upon the requirement, and as per the requirement we should be able to change the series compensation. So compensation of transmission line by series capacitor is likely to result the following advantage, that is it enhances the base power flow and loadability of the series compensated line. It results in the additional losses in the compensated line from the enhanced power flow. This power flow will increase automatically. Additional losses will also be increased. It results in the increased responsiveness of the power flow in the series compensated line from the outage of the other lines in the system. Now, what are the different advantages of this TCSC? It is, it is a rapid continuous control of the transmission line series compensated level. The dynamic control of the power flow in selected transmission line within the network to enable optimal power flow conditions and prevent loop flow of the power. So it means that it is for an interconnected system. So we'll be able to perform the optimal power flow for the different transmission lines, and it also prevents the loop power flow. That means it may sometimes happen that sometimes the power flow in the loop, if we have a different transmission lines, we can say interconnected transmission line, the power may flow in the loop. It will be we can see by changing the reactance of this line by the capacitor, that power flow may be changed and loop power flow may be prevented. So damping of the power swing from the local and inter-area oscillations, because as power is changed there will be some oscillations of the rotor around the new steady state position. So but before coming to the steady state position, it results in some oscillation. That oscillation will be damped faster because of this series capacitor. So one more thing, suppression of the subsynchronous oscillations. This is one more thing which I actually did not explain here. What are the subsynchronous frequency and subsynchronous resonance or oscillations? But for the time being, you should just keep in mind that it results in the suppression of these oscillations. At subsynchronous frequencies, the TCSC presents an inherent resistive-inductive reactance. The subsynchronous oscillation cannot be sustained in this situation and consequently get damped. These also result in damping of the subsynchronous oscillations. Decreasing DC offset voltages. The DC offset voltage invariably resulting from the insertion of the series capacitor can be made to decay very quickly within few cycles from the firing control of the TCSC thyristors. So by controlling the alpha, or we can say firing of the thyristors, this DC offset voltage can be minimized. Voltage support. The TCSC in conjunction with a series capacitor can generate reactive power that increases with the line loading. Definitely, because it depends upon the square of the current. As current increases, this reactive power also increases, thereby aiding the regulation of local network voltages. So we can say voltage will be, it will automatically take care of the voltage. And in addition, the elevation of any voltage instability will also be prevented. Reduction of the short circuit current. One more advantage is that during the events of the high short circuit current, the TCSC can switch from the controllable capacitance to controllable inductance mode. So in that case, you'll see that it can be changed from controllable inductance mode, inductive mode. So an inductance will come into picture and it will be in series with the line, and the overall inductance of the line will be increased. That means the fault will be then decreased because of the increase in this inductance. Definitely the power transfer during this period of the fault will be zero. The only concern for this case here is the fault current, since it will act as an inductance in that case. So the inherent inductance of the transmission line plus this inductance will result in the decrease in the overall fault current. So it will restrict the short circuit currents in that way by changing from capacitive mode to the controllable inductive mode. Now let us come to the basic principle of operation of TCSC. As we know that TCSC is a capacitive reactance compensator which consists of a series capacitor bank. We just have shown here a capacitor shunted by a thyristor control reactor, that is TCR. This is actually TCR. In order to provide a smoothly variable series capacitor reactance. So when we change the reactance of this, the overall reactance or capacitor reactance of this combination will change, so that we can have a controllable and smooth variable series capacitor reactance. So the overall you can say impedance of this circuit will be given by 1 by j omega c. It should be 1 by j omega c into j omega l, sorry, parallel to the j omega l. So overall combination will be like this, minus g into 1 divided by omega c minus 1 by omega l. When you consume the minus inside this, it will be equal to j into 1 divided by 1 by omega l minus omega c. So 1 by omega l is nothing but BTCR, 1 divided by BTCR minus BC. So XTCSC will be equal to 1 divided by BTCR minus BC. This actually BTSC will be equal to BC minus BTCR, but XTCSC will be equal to minus 1 divided by BTSC. So in that case, you will see that it will come out to be this way. Here, this BTCR will be again equal to the same value. It will have the same value of this, that is this BL into 1 minus twice alpha by pi minus sine of 2 alpha by pi is 2 alpha. So when you convert it into XL alpha will be equal to XL into pi divided by pi minus 2 alpha minus sine of 2 alpha. Why this XL vary when alpha is equal to 0, BTCR will be equal to maximum value, and this XL will have a minimum value of this XL alpha will have minimum value of XL. When BTCR has an alpha value of 90 degrees, this BTCR will be equal to 0. So this whole will be equal to 0. So this will be equal to 0. This then will be equal to infinity. That's how it has been shown like this. So keeping these things in mind, we can actually see how this operates for different values of alpha. So the basic idea behind the TCSC scheme is to provide continuously variable capacitor by means of partially cancelling the effect of compensating capacitance by the TCR. Because here this I line current will be equal to this IC plus IT, and this IT is dependent upon the value of this BTCR. As BTCR will change, this IT will change, and overall current, that is this I line, will change, because this I line will be equal to IC plus IT, so their phasor sum will change accordingly. So if IC is greater than this IT, it will be total capacitive in nature. If this IT is greater than this IC, then it will be inductive in nature. So usually we avoid this IC to be equal to IT, that is the resonance condition. In that case, this BTCR will be equal to BC, which is known as the parallel resonance condition. So TCR at a fundamental system frequency is a continuous variable reactive impedance. We know that, controlled by the delay angle alpha. The steady state impedance of the TCSC is that of the parallel LC circuit. That is, this will be a parallel LC circuit at steady state, consisting of a fixed capacitor whose impedance is XC and a variable inductive impedance whose impedance is by XL alpha. That is, the total reactance of the system will be given by a parallel combination of these two. So the TCSC thus presents a tunable parallel LC circuit to a line current that is substantially a constant alternating current source. That means, let us say this is a constant current source, so it will act as a variable impedance for this current source. As the impedance of the controllable reactor, XL is varied from its maximum infinity towards its minimum omega L. The TCSC increases its minimum capacitor impedance, that is XTSC, that's equal to XC, it's equal to 1 by omega C, and thereby the degree of series capacitor compensation, until the parallel resonance at XC is equal to XL alpha is established. So, and XTSC is maximum theoretically becomes infinite. What does this mean? That means when XL is varied from the maximum value, that is infinity, it will be infinity when BTCR is 0, and we know that BTCR will be 0 at X. This alpha is equal to 90 degrees or 180 degrees with respect to origin. So in that case, this will be infinity. When this is infinity, BTCR will be 0, so XTCSC will be equal to only XC, that's equal to 1 by omega C. So 1 by omega C, magnitude will be 1 by omega C. We are not taking into consideration the value of minus at that time. And thereby the degree of the series capacitor compensation. So we change the degree of series compensation as well. Until the parallel resonance, we start from 0 and then try to increase the BTCR or decrease the this XL value. When we increase this BTCR from 0 to when its value is equal to BC, at that time it will result in resonance. Resonance means in that case XTCSC will have a maximum value of infinity. So we'll say that at that time this is a minimum value, it says a minimum value, maximum value at this end. So it will be infinity. And then decreasing XL alpha further, the impedance of the TCSC becomes inductive. So from BTCR is equal to 0 to BTCR is equal to BC, the capacitance BTCR is slightly less than BC, the capacitance will be, the reactance of this system will be capacitive in nature. Now, when alpha is decreased beyond the value at which BTCR is equal to BC, so this BTCR will now increase as alpha is decreased. When it will be increased, it will be greater than BC and it becomes inductive. Reaching its minimum value, XL parallel XC divided by XL minus XC at alpha is equal to 0. That means at that time this XTCSC will have a value of this will be having a value of BL, that is BL 1 divided by BL minus BC at alpha is equal to 0. While the capacitor is in effect bypassed by TCR. We can say in that case maximum current will be flowing through this and capacitor will be effectively bypassed by the TCR. It is because we are making this the value of this inductive reactance, so this capacitor very small as compared to this, so that when this comes into picture, the full conduction of this takes place, almost all the current will flow through this, bypassing this capacitor. Therefore, with the usual TCSC arrangement, in which the impedance of the TCR reactor XL is smaller than that of the capacitor XC, the TCSC has two operating range around it is internal circuit resonance. One is that alpha C limit less or equal to alpha less or equal to pi by 2. So we'll start from alpha, this the value of this at 0, that means alpha will be equal to pi by 2 up to the value of this at which alpha BTCR is slightly less than this BC to avoid this resonance. So in that case, in that lesser case, that BTCR is slightly less than BC at an alpha, we call that alpha as alpha C lim. So up to the value of alpha C lim to the value of this pi by 2, you will see that we have a BTCR at this value it has 0, at this value it will be slightly less than this, so the overall value of this will be negative. That means it will be capacitive in nature. So that means from alpha C lim to pi by 2 for the change in alpha, you will see the overall reactance of this combination will be capacitive in nature. So the change in capacitance will be like this, because earlier it will be capacitive when this is 0 minus 1 by BC, and then it will increase, and then it will increase as this increases, because you will see that it is coming closer to this. For example, if BC is 10, if BC is 10, 1 by 10 is, let's say, 0.1 minus 0.1, and it's in minus, it is in we can say this fourth quadrant. When BTCR is again, let us say, equal to 5 minus 10 is equal to minus 5, it becomes minus 1 by minus 5, it becomes minus 0.2, so it has increased. When it becomes, let us say, 9, so 9 minus 10 is equal to 1 minus 1, so it becomes exactly minus 1. So when it becomes very close to this, that is, let us say it is 9.9 minus 10, it will equal to 1 divided by 0.1, it will equal minus 10. So then it will increase sharply as it will go close to this. So when this is equal to this, it will be minus infinity, go to this way. Similarly, When this is very close to the value of this but slightly greater than this, it will have a positive value, but it will be having a value which is goes to infinity. Let us explain it. When this is having a maximum value at alpha is equal to 0, and this is a maximum value alpha is equal to 0, this will be greater than this, since we are making this by design. So in that case, this BTCR minus BC will be positive, the overall term will be positive, will be inductive in nature. As it is alpha is increased, this BTCR will decrease. Again, let us say it is maximum value is 20 and it is decreased to 15. This value is 10. 15 minus 10 will be equal to 5. So 1 by 5 is 0.2. When it is made to come close to this, let us say it is equal to 11. 1 by 11 minus 10 is 1, that it will come to 1. Let us say it is equal to 10.1. 1 divided by 10.1 minus 10 is 1 divided by plus 0.1, that is equal to 10. So as it goes to close to BC, it will goes to infinity, very high value. So by restricting its value from alpha lim to alpha C lim, we are actually restricting it to go to close to resonance. So in inductive range, its value or its range will be from 0 to alpha L limit, and in capacitive range, its value will be alpha limit to pi by 2. That is given over here. This is for capacitive range and this is for inductive range. So I hope you understood its basic principle of operation, and this the x versus alpha graph as well, or we can say x versus alpha characteristics for this case. So here usually we never talk about in terms of susceptance, because we are actually interested directly in the reactance of the this TCSC, because it is ultimately TCSC which actually directly controls the power, or we can say real power, which is given by V1 V2 by x sine of delta. It is this x which is coming into denominator. That's why we directly talk about the value of this reactor. Now in practical TCSC, apart from this capacitor and TCR, we have some other components which are working in conjunction with this, you can say, TCSC, and they are very important. So a practical TCSC module also includes protective equipment normally installed with series capacitors as shown in the figure. We have a circuit breaker, we have MOV, that is metal oxide varistor, we have the simple capacitor, and we have ultra high speed contact, which is bypassing, which is used actually to bypass the switch. So we have a metal oxide varistor, essentially a non-linear resistor. It is connected across the series capacitor to prevent the occurring of high capacitor over voltage. For example, if high voltage appears across this, since this is a non-linear resistor, for lower value of resistance, it acts as an open circuit. For higher value of resistances, this voltages, it acts as a short circuit. So in that case, for higher voltages, this capacitor will be short circuited. So finally, for lower voltage, it will be prevented from being damaged. Not only does the MOV limit the over voltage across the capacitor, but it allows the capacitor to remain in circuit even during the fault conditions to help improve the transient stability, because in the fault condition there will be less voltage that will appear across this, so it will not bypass this capacitor at that time, because it has to maintain the voltage at that time to prevent or to improve the transient stability. Also installed across the capacitor is a circuit breaker for controlling its insertion in the line. If the circuit breaker is closed, you will see that circuit breaker will be bypassed. There will be no can say circuit breaker which we can see it is in the line. When circuit breaker is open, circuit breaker this will come in the picture. It is connected in series with the line. In addition, the circuit breaker bypasses the capacitor if severe fault or equipment malfunction event occur. So if fault occurs, this is closed, the fault current will flow through this will be prevented from being damaged. And this LD is in that case connected in series with this so as to limit the fault current. If the TSC vault is required to operate fully on mode, in that case, instead of using these switch, because ultimately they are we can see a lot of losses in switching, losses are occurring in these switches, so it is better to use ultra high speed contact to close this, to bypass this, If it is fully on mode for prolonged duration, in that case the conduction loss are minimized by installing this UHSC switch, which is used across this wall. So these are some protection equipment that are used along with the TCSC so as to improve its performance. Now there are different modes of operation of this TCSC. One mode is the bypass thyristor mode. So we have already discussed it, but here we'll discuss in more detail. In this mode, the thyristors are made fully conduct with a conduction angle of 180 degrees. That means sigma will be equal to 180 degrees and alpha will be equal to 0 degrees. Gate pulse are applied as soon as voltage crosses the thyristor. Thyristor reaches 0 and becomes positive, resulting in the continuous sinusoidal flow of current through the thyristor valves. So in that case, there will be a continuous current through the thyristor valves. They will be, and since we know that the reactance of this is less as compared to this, or the susceptance of this is more as compared to this, most of the current will flow through this inductor circuit. The TCSC module behaves like a parallel capacitor inductor combination. However, the net current through the module is inductive, for the susceptance of the reactance is chosen to be greater than that of the capacitor. I have just told you. Also known as a thyristor switch reactor, that's in this case it will be used as a thyristor switch reactor. It is triggered as alpha is equal to 0. The bypass thyristor mode is distinct from the bypass breaker mode, because if we use a breaker, that is the circuit breaker that we have just discussed, in which the circuit breaker provided across a series capacitor is closed to remove the capacitor or TCSC module in the event of TCSC fault or transient over voltage across the TCSC. So this sentence actually try to differentiate the bypass breaker mode and thyristor switch reactor mode. In that case, you will see almost both the things or both the modes are almost same, but you will see that in the bypass breaker mode, this will not come in picture, but in this mode, some current will flow through this. So that is the main difference between the bypass breaker mode and thyristor switch reactor mode. Another thing is the block thyristor mode. This is very simple. In this mode, that's also known as waiting mode. The firing pulses of the thyristor valves are blocked. We're not giving firing pulses to these thyristors, or we can say BTCR will be equal to 0. So, or this will act as an open circuit. If the thyristors are conducting and a blocking command is given, the thyristors turn off as soon as current through them reaches 0 crossing. The TCSC model is thus reduced to a fixed capacitor, that is, this capacitor will be only present, and the net TCSC reactance will be capacitor, that will be equal to 1 by omega C. In this mode, the DC offset voltage of the capacitor is monitored and quickly discharged using the DC offset control. This is some different control, but you just remember this without causing any harm to the transmission system transformers. Because DC offset has a problem with the transformer, it saturates the transformer core. Now, partially conducting thyristor or vernier mode. So in this case, this alpha may be in between 0 and 90 degrees. This mode allows the TCSC to behave either a continuously controlled capacitive reactance or as a continuously controlled inductive reactance. It is achieved by varying the thyristor pair firing angle in appropriate range. However, a smooth transition from capacitive to inductive mode is not permitted because of the resonant region between the two modes. It is because of this region, because if we change the alpha smoothly from 0 to 90 degrees, there will be a region or a point where a resonance occurs. So to prevent resonance in the alpha equal to alpha r, that's the resonance value of the alpha, is actually prevented by taking a range where alpha is not allowed to, or we can say the thyristor is not allowed to fire between this alpha, that's alpha L limit to alpha C limit. A variant of this mode is the capacitive vernier mode. That means in this case it will act as a capacitive reactance. So in this case, the control is done in such a way so that the alpha will be equal to this alpha C limit to this pi by 2. In that case, it will be a vernier mode. So in this case, for this capacitor voltage and the capacitor current will have opposite polarity. This condition causes the TCR current that has the direction opposed to the capacitor current, thereby resulting in the loop current flow in the TCSC controller. So in this case, this capacitive reactance will be capacitive current will be more as compared to inductive current. So total current will be having this direction. The loop current will have this direction. Again, to preclude or to avoid the resonance, the firing angle of the forward facing thyristor are measured as measured from the positive reaching zero crossing of the capacitor. It's constrained in the region alpha C limit to 180 degree, or with respect to peak, with respect to origin, or alpha C limit to pi by 2 or 90 degree with respect to peak. So I'll write it here 90 degrees only, because we are in continuously seeing that it is with respect to peak. This construct provides a continuous Fourier control of the TCSC module reactance. The loop current increases as alpha is decreased from this 90 degrees to, I will again write it as 90 degrees to alpha C limit. The maximum TCSC reactance permissible with this alpha is equal to alpha C limit is typically 2.5 of 3 times the capacitor reactance of the fundamental frequency. So this we have already discussed. The capacitance will increase up to this, and this is the maximum value for capacitance. Another variant is the inductive vernier mode, that is the inductive mode, in which the TCSC can be operated by varying the high level of the thyristor conduction. So thyristor conduction will be increased now, or we can say this inductor current will increase. You can see that when inductor current increase, the loop current will for this flow through this, or we can say loop current will have this direction. In this move, direction of circulating current is reversed, and the controller presents a net inductive impedance. We have a net inductive impedance in this case. So based on these three modes, thyristor valve operation, two variants of the TCSC emerge. One is thyristor switched series capacitor, which permits a discrete control of the capacitive reactance. That means either the capacitance, either the value of the reactance is in circuit, as if there are no thyristors, or it is not there in the circuit, as if we have a closed switch, or we have thyristor control series reactance, which offers a continuous control of capacitance. In this case, alpha will be equal to 0 or 90 degrees. In this case, alpha will be between 0 and 90 degrees. We have already discussed this as well. Now the VI characteristics of the TCSC is shown in this. You will see in inductive mode, it will be identical to that of the TCR if this limit is not there. If this limit goes exactly to, we can say 90 degree, it will we can say coincide with this, and it will be identical to that of TCR. Since we are changing this alpha is equal to 0 degrees to alpha is equal to alpha limit, this will be its operating range, where this determines its operating range, or we can say a VL max. And from this point to this point, it is operating, or it is making the voltage constant. Similarly, for capacitive, it will be again similar to that of the TCR. We are characteristic for a constant voltage, but the only thing is that it will be from this point to this point, or again this region would have been if there would not have been any resonance. So in that case, when it's a alpha C limit, you will see that we have this range more slope. Alpha C limit have more capacitance, we have this more slope, this has a less slope, and from this to this we have a constant voltage. This is equal to alpha is equal to 90 degrees. When alpha is equal to 90 degrees, we have only capacitance in the circuit. When capacitance are in the circuit, you can say capacitive voltage and capacitor current, they will vary linearly, and this slope will determine the capacitance. This slope also will determine the capacitance, because it's a capacitive in nature, and this alpha is equal to alpha C limit, it will be a constant capacitance. And in between this and this, we try to change the alpha in such a way so that the net voltage will remain, VC max will remain constant. Similarly, for this case, we change alpha from alpha is equal to 0 to alpha lim, so that the voltage will remain constant, because you will see that from this point to this point, current decreases, but voltage remains constant. That means from this point to this point, this reactance will increase, and this reactance has to increase, because for alpha is equal to 0, its BTCR is maximum but reactance is minimum. So as it decreases, its reactance will increase to make this voltage constant. This is actually for the system where the voltage is not maintained constant. this is the value for alpha is equal to alpha limit, this is the value for alpha is equal to 0, and these are the values for you can say maximum current values. So we cannot go beyond this value because we have alpha is equal to this alpha limit, it's a limited value, and we cannot go beyond this because alpha will have, when alpha is equal to 0, this XL will have some finite value and it has some finite slope. So its operating region, inductive region, will be from this point to this point. This is without voltage control. Similarly, in capacitor, we have XC maximum for alpha is equal to XC limit, and for alpha is equal to 90 degrees, it will have minimum capacitance, and range will be from this point to this point. This will be without voltage control, but this will determine it's the maximum current, and this will determine the maximum voltage here and here. But this is the this voltage control. Now, this is already actually discussed. This is actually derived from the same. This is a you can say X versus I graph, that is the XTCSC and the current flowing, the total current flowing through this. You can see, so this is the XL max. Let us first discuss about this. When current increases from XL min for alpha is equal to 0, you see the current increases, this X remains constant, and this will determine this line because current increases, this is constant. This is constant up to I max, we get the maximum voltage, that is this line. So for alpha is equal to 0, and for alpha is equal to 0, we know that X will be equal to XL minimum. When it reaches to this value, after that, you will see that if at this point, now the current will decrease, that the current will decrease. We want that the voltage will remain constant. Well, current decreases, we decrease the value of alpha. When alpha decreases, you can see from here, current decreases, alpha has been decreased, because from this to this, alpha will be continuously decreasing up to alpha L limit. Sorry, alpha will be continuously increasing from alpha is equal to 0 to alpha is equal to alpha limit. Well, alpha is decreasing, sorry, alpha is increasing. In that case, BTCR will decrease. When BTCR will decrease, but this XL will increase. When this XL will increase, you can see up to this point, this XL will increase and will reach at this point XL max. This is the XL max at alpha is equal to alpha limit. And even if then this decreases, you can see that when the current decreases, this remains constant. When current decreases, this remains constant for this decreased current. This is, or you can say, this has been taken. This is the change in the reactance of the TCR with alpha as current decrease from I max to 0, and as alpha change from 0 to this alpha mean for constant voltage or voltage control. Similarly for XC, so XC maximum for we can say let us say XC minimum, we discuss from XC minimum. This is for alpha is equal to 90 degrees. When current increases from 0 to this I max, this will remain constant, will not change. So this line corresponds to this line. As current increases, voltage increases linearly. Now let us say at this point current decreases. Now we want that the constant voltage should appear. Voltage control should be done. So voltage control should be done by increasing the capacitance. As current decreases, capacitance will decrease. Capacitance will increase. Current decrease, capacitance increase, so as to keep this constant. Since that alpha is equal to alpha C limit, XC has the maximum capacitance. After that we cannot increase it. So as current decreases, you can see this line goes to this voltage decreases, but this remains constant. So this is how this X versus I graph will look like, and this is the graph of we can say VI characteristic for voltage control. So I think this is enough for today. I'll stop here. Thank you.